Over the last 2 episodes, we tore the database apart and matched different data to different kinds of databases. But there's one kind of waste that's been sitting there the whole time. The same question, asked 10,000 times, and your system dutifully computes it from scratch every single time. A cache does exactly one thing. It stores the result you already computed and puts it right up front. Next time it's asked, it just hands it back. No more reaching to the back end. But there's an old saying. The 2 hardest things in computer science. One is naming things, and the other is cache invalidation. Today, I'm actually going to run it for you. Just how fast it can be, and just how badly it can burn you. First, let's weld one sentence about caching into place. A cache trades space for time. Go one level deeper. It's trading you might read a stale value for that speed. So when you use a cache, from start to finish, you only ask 3 questions.
1. Where to cache? Client, CDN, web tier, in front of the database, or inside the app. 5 places it can live. 2. How to write? Write through, write back, or cache aside. 3. When to invalidate it?
Where to cache, how to write, when to invalidate. These 3 decide life or death. Let's start with the most common one, cache aside. The logic is dead simple. Ask the cache first. If it's there, take it and go. If it's not, then hit the database and backfill the cache on the way. I'll demo with a slow database, 10 milliseconds per query.
First request, cache is empty, hit the database, 12.5 milliseconds. Second request for the same thing, served from cache, 0.58 microseconds.
About 20,000 times faster. But don't celebrate too soon. A cache's entire payoff rides on one number, the hit rate.
I ran 2 access patterns, one with concentrated hotspots. 80% of requests hit 20 hotkeys. Hit rate 93% and an average of 0.82 milliseconds per request. Switch to uniform random, hit rate 1%, average 12 milliseconds. Same as no cache at all.
Get this one line. Whether a cache is fast has nothing to do with the cache. It depends on whether your access has hotspots. No hotspots in your data, and the cache is useless, just wasting memory. Second question, how to write? This one is a trade between consistency and speed. 2 mainstream approaches.
Write through. On a write, you write the cache and the database together, and it's not done until the database has it on disk. 12.5 milliseconds per write. Consistent, but slow. Write back. Write only the cache, mark it dirty, and flush it back to the database asynchronously later. 0.9 microseconds per write, over 10,000 times faster.
Write back is that fast, so where's the cost? The cost is you're betting your data's life.
I wrote 20 records, all sitting in the cache. The background just flushed 8 back to the database, and right then, the process crashes. The database has only 8, and the cache is gone. 12 records you already told the user were saved, gone.
That window where the dirty pages haven't been flushed back, that's your data loss window. Write back is fast, but you're gambling with durability. For critical writes, play it straight and use write through. Third question, the one that old saying called the hardest. When to invalidate. Let me show you a trap that almost every high concurrency system has fallen into. One really hot key, and its cache expires. At the exact instant it expires, 100 requests arrive at once.
Each request looks, sees nothing in the cache, and goes, fine, I'll hit the database and compute it myself. 100 requests hit the database 100 times, all crammed into that one moment of expiry.
This is a cache stampede, also called a thundering herd. One key expires, and it's like kicking a hornet's nest. How do you fix it? One word. Single flight.
Let the first one in do the compute. The other 99 don't all rush the database, they just wait for its result. Database hits drop from 100 to 1.
And invalidation itself is hard, no matter what. Set a TTL, and it's easy, but the moment it expires, you get a stampede. Delete the cache yourself after you update the data, and it's accurate, but write the database first, or delete the cache first. Get the order wrong by one step, and you read stale data. That's why the old-timers call it one of the two hardest things. Same as always, one question. How will AI change this part? This time, what it changes is the definition of the word hit.
In a traditional cache, only an identical request counts as a hit. But with large language models, a user asking, how do I reset my password and I forgot my password? What do I do mean the same thing? A semantic cache says, close enough in meaning counts as a hit, and it just hands you last time's answer.
Let me demo it. The cache holds 3 question and answer pairs, and 7 differently worded questions come in.
Exact cache. 0 out of 7. Reword it and it all misses, and each one costs another large model call. Semantic cache. 4 out of 7. Similar phrasings, just reuse the answer.
Every large model call is real money, and reusing one is money saved. This is the killer cost saver of the LLM era. But let me draw the boundary hard for you.
Loosen the threshold, and how do I change my password gets treated as how do I reset my password?
Changing a password and resetting one aren't quite the same thing, but they get treated as one, giving you an approximate and possibly wrong answer. So a semantic cache only works where you can tolerate approximation. Threshold, recall, and false hits, that's its trade-off triangle. While you save money, you're also betting on correctness. Same philosophy of approximation as that vector database from last episode. Finally, let me flag a few traps.
1. A cache is not a silver bullet. At cold start, it's all misses. A low hit rate means you added it for nothing, and you still pay for the memory. 2. Invalidation is harder than you think. Double write inconsistency and cache stampede, they all live here. 3. You have to genuinely accept reading stale values. A cache's speed is, at its core, bought with exactly that.
In one sentence, don't cache things that shouldn't be cached just for the sake of speed. Let's wrap up. Caching is, once again, a trade of consistency for speed. You'll notice that everything in this course so far has been a trade. And using it well comes down to the same 3 questions. Where to cache, how to write, when to invalidate. Get these 3 clear, and a cache is a superweapon. Get them wrong, and it's the #1 source of your production incidents. By now, your system has several kinds of databases, with a cache standing guard out front. With this many parts, how they talk to each other, and how they keep from dragging each other down is a whole new problem. Next time, we'll talk about the thread that strings them together while keeping them decoupled. Async and message queues.